Welcome, geniuses. This is a preview of first semester calculus next year. This follows up our JTBs. Some of the information in here, some of the problems will actually require less work than our JTBs do, but some will also move us more into a real world environment where calculus starts to get pretty interesting. Let's go ahead and get started here. Find the average rate of change over the interval. So for instance, from time 0 to 2, we're going to put 0 in here, 2 in here, and we're going to see how far we changed, and we know it took 2 days or 2 seconds. It's sort of equivalent to saying we traveled 150 miles in 3 hours. I don't know how I got there. All I know is that 3 hours down the road, I was up at 150. Maybe I went really fast, took a lunch break, and then kind of fast and slowed down a little bit. Doesn't matter. I could have gone really slow. I just know that I traveled 150 miles in 3 hours, so miles per hour, we averaged 50. No matter how we got there, we averaged 50 miles per hour, assuming we didn't go backwards at any point. So let's take a look. I want to put 0 in, number 2. I want f of 0, which is square root of 4 times 0 plus 1, or square root of 1, or just 1. And then f of 2, I get square root of 4 times 2 plus 1, square root of 9, I get 3. So how far did we move from time 0 to time 2? Our change of y is 3 minus 1, and our x's changed 2 minus 0. So we end up with 2 on 2, or 1. The average rate of change is just 1. Now, don't assume that's going to be the same for 10 through 12. I'm only going to do portions of this to give you a good feel what we're doing, but the process would be very similar. In fact, I will go ahead and do that one just to emphasize. So here's B. F of 10 gets us square root of 41, 40 plus 1. F of 12 gets us square root 48 plus 1, 49, or 7. What's our average rate of change? It would be, we ended up at 7, we started at square root of 41, we ended up at 12, x's ended up at 12, started at 10, so it's 7 minus square root of 41 on 2. And we can put that in decimal if need be. Okay, let's jump to 3. I'll go 3b, just showing some examples here. I want f of 1. F of 1 is e to the first, or e. F of 3 is e to the third. So average rate of change, the y's, change of y's changed into e to the third from e, as the x is turned into 3 from 1, or e to the third minus e on 2. Okay. And let's look at 5. I'm going to go with 5b. I'm going to write this down here, f of x, just so I can zoom in a little bit. F of x equals cotangent of x, and b, the interval is pi on 6 until we get to pi on 2. So let's take a look there. Create some space here. So f of pi on 6 gets us cotangent of pi on 6 square root of 3 to 1, and f of pi on 2, x to y is 0, on 1, 0. That's cotangent of pi on 2 is 0 on 1, 0. So our average rate of change, average rate of change is going to be the y's changed into 0 from square root of 3 as the x's turned into pi on 2 minus pi on 6, or negative square root of 3, let's see here, on 3/6 minus 1/6, 3/6 minus 1/6, 2/6, or 1/3 pi on 3, so we end up with negative 3 square root of 3 on pi is our average rate of change. And again, we got some more problems to do there, but everything I think is pretty well represented. Some of these back of the book or answer keys might be rounding to decimals. Okay, at the indicated point, find the slope of the curve. Let's start with 10. Y prime, the first derivative, because we're looking for slopes, is 2x minus 4. At x equals 1, the slope at that point would be 2 times 1 minus 4, or negative 2. There's the slope of the curve at that point. B, equation of tangent line. Well, I need the point, so the point is 1 something. If I put 1 in here, I get 1 squared 1 minus 4 times 1, 4. 1 minus 4, negative 3. So the tangent line is y minus negative 3 equals our slope, our rate of change, negative 2 times x minus 1, which of course we could put that in a variety of different forms. Okay, and C, an equation of the normal. Here's a curve. I didn't need to have it on any place in particular. Here's a tangent line. The normal is the perpendicular line to it, but it still goes through the same point, so that would be y plus 3, equals something times x minus 1, but I just need to be perpendicular to it, and perpendicular to a slope of negative 2 is a slope of opposite reciprocal positive 1/2, and we're not going to draw the graph for the purpose of this assignment. Let's take a look at 11. I'm going to think of y as, I'm not finding the derivative yet, as x minus 1 to the negative first. As I'll frequently say, you get a problem like this, you want a quotient rule, be my guest. I'm not even trying to argue that my way is better, but this is an option. I'm going to chain rule this. First derivative is the outside derivative, negative 1 times something to the negative second of the inside function, times the inside derivative, but the inside derivative is just 1. So we get, first derivative is negative 1 on x minus 1 squared, exactly what we would get if we quotient ruled that. So I want to know what the slope is at x equals 2. And we put 2 in, and we get negative 1 on 2 minus 1, 1 squared 1, we get negative 1. And f at 2, if I put 2 into this function, we're at the point 2 something, 2 what? 1 on 2 minus 1, 1 on 1, 1. So B, our tangent line, is y minus 1 equals slope negative 1 times x minus 2. And the equation of the normal passes through, sorry if that was out of view, my mistake. If you want to pause that and get caught up here. Pressed for time a little bit and got careless there, my mistake. Okay, if we want to find the normal, same ordered pair, y minus 1 equals something times x minus 2, but opposite positive, reciprocal of 1, 1, positive 1. And the 1, of course, is there just for emphasis. Okay, I'll be careful here. I'm really overall not too interested, other than a little bit of maybe the discussion that we have in class about 19 through 22. So I'm going to jump to 24. These problems are much less than what we were doing in the JTB. We're just supposed to find the rate of change the slope at the given time. To find the slope, we're going to use slope formula or derivative. F prime of t equals 6t plus 2 at t equals 3, or f prime of 3 is 6 times 3, 18, plus 2, 20. That's our instantaneous rate of change. Now that might be feet per second. We don't know, but that's where we're headed. For 25, f of t is t plus 1 on t. I'm going to go ahead and quotient rule this one. Low, derivative of high is 1, minus high, t plus 1, derivative of low is 1, over the square of the thing below. So careful here, very common mistake would be to not put the parentheses or to not distribute that negative. I get t, minus a t cancels. I get minus 1 times 1, minus 1 on t squared. And I want to know what that slope is at t equals 2. So that is negative 1 on 2 squared, 4. Simpler than our JTBs. All right, some word problem goodness here. An object is dropped from the top of a 100-meter tower, and its height, which I'm going to refer to as this formula as h equals, since it's height, is 100 minus 4.9 t squared. How fast is it falling 2 seconds after it drops? How fast? Fast is speed. And I've got height and being graphed versus time. Height divided by time, or meters per second. That is a derivative. Slope is a derivative. So I want h prime, or change of h, dh we call it, on dt. That's the same as h prime. So dh dt, the height changes as the time changes, is derivative of 100, 0, derivative of negative 4.9 t squared is negative 4.9 times 2, negative 9.8 t to the first. At t equals 2, we get negative 9.8 times 2, or negative 19.6. I'm tempting to say that's meters per second, which would not be entirely wrong to say that. However, how fast is it falling? The falling builds in the negative already. So how fast is it really traveling? It's really traveling at 19.6 meters per second. See, if it said how fast is it rising, then we would need to say negative 19.6. Because it's not rising, it's doing the opposite of rising. All right, that's all there is to that one. 28. Rocket launch. At t seconds after liftoff, the height of the rocket is 3t squared feet. How fast is it? So here again, we would have height in feet over time in seconds. Slope is feet per second. Y's on x's. I want the derivative. So change of height over change of time is 6t. At t equals 10, we get 6 times 10, 60. How fast is the rocket climbing? Yeah, it's climbing at 60 feet per second. Now, want to assure you that if you are in good shape on 27 and 28, 31 and 32 are complete redos of those problems. Just very, very common introduction into some simple derivative calculus work. Let's look at 30. As you can see, 29, 30 pretty well modeled together. The volume of a sphere. Volume equals 4/3 pi r cubed. Didn't have a lot of people in class remember that one. Understandable. Once you're into calculus, you'll probably be working with spheres enough, it'll just kind of sink in. What's the rate of change, the slope? We're going to work with derivatives here of the volume. Now, take a look at this. Of the volume with respect to, pay careful attention. We know we want derivative. We want dv. Now watch. dv with respect to. With respect to. You see with respect to, that is your fraction line. The radius. So they're asking how fast is the volume changing based on the change of radius. Now, the volume is going to change in inches cubed. The radius is just the length is going to change in inches. That is our unit rate for our solution, inches cubed per inch. We don't want to reduce that. It doesn't tell the story. Inches cubed. The volume changes in inches cubed as the rate changes in inches. All right, let's get to it. dv dr. That's the derivative of v on this side. The derivative with respect to r, 3 times 4/3, 4 pi r squared. At r equals 2 is 4 times pi times 2 squared, or 4 times 4, 16 pi. 16 pi inches cubed per inch versus area of a circle. Area equals pi r squared. dA dr, change of area based on change of radius as we're reading this. What is the rate of change of the area, dA, with respect to the radius? So this would be 2 pi r. Area is changing ... in square inches as radius is changing in plain old inches. And again, we don't want to reduce that, and I'll leave that to the reader. 31, 32, very, very similar to 27, 28. 33, very similar to 34. Horizontal tangent line could look like this, or this, or this, or this, or this. Horizontal lines have a slope of 0. I think I want to find out when the slope is 0. F prime of x equals -4 minus 2x. -4, set that equal to 0. -4 equals 2x, x is -2. At what point, not what x value, what point? -2 something. 3 minus 4 times -2 minus -2 squared, that's 3 plus 8 minus 4, 11 minus 4, 7. There it is. Okay. Pretty well prepared if our JTB work went well, and if your JTB didn't go well, it ended up going well. Now we're used to finding like tangent lines when a slope is 0. No different here, other than we're finding the tangent line, and now the slope's -1. For some reason, I guess we're interested in, here's about a -1 slope. We're interested in finding tangent lines that have slope of -1. So let's go ahead and find the slope formula. I'm going to treat this as y equals x minus 1 to the -1st and chain rule it for y prime. Y prime is -1, leave the baby alone to the -2nd, treat the baby times 1, or -1 on x minus 1 squared. Going well. I want to know when that -1 on x minus 1 squared equals -1. I'm going to cross multiply, and I get negative this equals -1, or x minus 1 squared equals 1. That would be x minus 1 equals plus or minus 1. We're going to be careful here. X equals, when I add 1 to 1, I get 2. When I add 1 to -1, I get 0. That's two different points. 2 something and 0 something. In the original equation, when x is 2, I get 1 on 2 minus 1, 1 on 1, 1. When x is 0, I get 1 on 0 minus 1, 1 on negative 1, negative 1. And the slope, we've made the slope be negative 1. So slope is negative 1, so my equations are y minus 1 equals negative 1 times x minus 2, and y minus negative 1, y plus 1 equals negative 1, slope is negative 1, times x minus 0, just for emphasis, I put the minus 0 there. So there's A. Now B, a normal line. By this time we know that a normal line, if I've got a curve, looks like this. Here's a tangent line. Normal lines are perpendicular to tangent lines at a point of tangency. Therefore, we're dealing with exactly the same points because this slope is the opposite reciprocal of that slope. If this was slope 2, we got to do all this work again and change this to 2. But since it's just perpendicular to, and this ended up with our slopes, when we calculated our slopes here, based on our slopes here, we just need to be perpendicular to, but it's going to be the same points, and we want a slope of 1. So B, y minus 1 equals 1 times x minus 2, and y plus 1 equals 1 times x minus 0, 0 for emphasis. And that is it. If you are looking for a challenge, this problem was made for you. We will go through that one in class, but there's a little bit going on. That's a pretty big jump from 35 to 36. I will tell you this. We know this graph starts up 9. This would be 3. This would be negative 3. And 112 might be somewhere around here. It's not on the curve. We're looking for, now this is just a diagram. It might not be drawn accurately. We're looking for trying to find out what these points are for our tangent line. So you got some work to do there. In past problems, they would have said, hey, here's a point that's on the curve. But this one's not even on the curve. So definitely a challenge and well worth the effort. We will go through that in class. Good luck. Let us know what we can help with.